Chemistry is the branch of science that focuses on the study of matter, which includes everything around us. The basic of chemistry revolves around the concept of atoms. Atoms are the basic building blocks of all matter. Atoms are incredibly small, so millions of them could fit on the tip of a needle. Despite their size, each atom has a complex structure made up of three main components: protons, neutrons, and electrons. At the center of the atom is the nucleus, which contains protons, positively charged particles, and neutrons, neutral particles with no charge. Nucleus is surrounded by electrons, which are negatively charged and move around in orbits or energy levels. You should not mix atom with elements. Actually, elements are pure substances made up of only one type of atom. Each element is defined by the number of protons in its atoms, which is unique to that element. For example, hydrogen has just one proton, oxygen has 8 protons, and carbon has 6 protons. When atoms combine with each other, they form molecules and compounds. Molecules are formed when 2 or more atoms bond together. These atoms can be of the same element, like 2 oxygen atoms joining to form an O2 molecule, or of different elements, like when 2 hydrogen atoms and 1 oxygen atom combine to form water. When atoms of different elements combine, they form a compound. Compounds are substances made of 2 or more different elements that are chemically bonded together in a fixed ratio. Water, for instance, is a compound made of hydrogen and oxygen, while carbon dioxide is a compound of carbon and oxygen. The key difference between an element and a compound is that elements consist of only one type of atom, while compounds are made from atoms of different elements. Ions and formation of ions. Ions are atoms or molecules that carry an electric charge, either positive or negative. They are formed when an atom gains or loses electrons. When an atom loses one or more electrons, it becomes a positively charged ion called a cation. For example, if a sodium atom loses 1 electron, it becomes a sodium positive ion. On the other hand, if an atom gains electrons, it becomes a negatively charged ion. For example, chlorine atoms can gain an electron to become a Cl negative ion. Molecular and empirical formula. The molecular formula of a compound shows the exact number of each type of atom in a molecule. It provides the actual composition of the molecule. For example, the molecular formula of glucose is C6H12O6, which indicates that each molecule contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. On the other hand, the empirical formula represents the simplest whole number ratio of atoms in a compound. It gives the proportion of elements but not necessarily the exact number of atoms. For glucose, the empirical formula is CH2O, since the ratio of carbon, hydrogen, and oxygen atoms is 1:2:1, which is the simplest form of molecular composition. Chemical bonding. Chemical bonds are the attractive forces that hold atoms together to form compounds. These bonds result from the interactions between the electrons of atoms, and they are essential for the stability of compounds in nature. Actually, the main reason of forming bond is to get stability. The 3 main types of chemical bonds are ionic, covalent, and metallic bonds. Ionic bonds is formed when one atom transfers electrons to another atom, creating charged particles called ions. This typically happens between metals and nonmetals. The metal atom loses electrons to become a positively charged ion, while the nonmetal gains electrons to become a negatively charged ion. For example, sodium chloride forms an ionic bond, where sodium donates an electron to chlorine. But covalent bonds are formed when 2 atoms share pairs of electrons. This type of bond usually forms between nonmetals. The shared electrons allow each atom to obey octet rule, and by doing so, they become stable. Covalent bonds can be single, double, or triple, depending on how many pairs of electrons are shared. An example is water, where oxygen shares electrons with 2 hydrogen atoms. And metallic bonds are formed in metals, where atoms share their outer electrons freely across a sea of electrons. This electron delocalization allows metals to conduct electricity and heat efficiently. Periodic table. The periodic table is a systematic arrangement of all known chemical elements, organized based on their atomic number, electron configuration, and recurring chemical properties. First developed by Dmitry Mendeleev in 1869, the modern periodic table arranges elements in rows called periods and columns called groups. Each element is represented by its chemical symbol. Periodic table is divided into several key components, such as metals, nonmetals, and metalloids. Metals are present at left side of periodic table, and nonmetals are at extreme right side, and metalloids are highlighted in separate line. All the elements having similar properties are placed in the same group. For example, Group 1 contains the alkali metals, which are highly reactive, while Group 18 consists of noble gases. Chemical reactions. A chemical reaction is a process in which substances, known as reactants, undergo a transformation to form new substances, called products. During a chemical reaction, the chemical bonds in the reactants are broken, and new bonds are formed in the products. These reactions involve the rearrangement of atoms, but no atoms are lost or gained, and obey the law of conservation of mass. Chemical reactions are represented by chemical equations where the reactants are shown on the left side and the products on the right, with an arrow indicating the direction of the reaction. For example, in the reaction between hydrogen and oxygen to form water, the equation is written as 2 hydrogen atoms plus 1 oxygen atom equals 1 water molecule. Some common types of chemical reactions includes synthesis reactions. In a synthesis reaction, 2 or more reactants combine to form a single product. For example, the formation of water from hydrogen and oxygen is a synthesis reaction. Decomposition reactions. In a decomposition reaction, a single compound breaks down into 2 or more simpler substances. For example, when calcium carbonate is heated, it decomposes into calcium oxide and carbon dioxide. Single displacement or substitution reactions. In these reactions, one element in a compound is replaced by another element. An example is the reaction between zinc and hydrochloric acid. Acid and bases. Acids are substances that release hydrogen ions when dissolved in water. They have a sour taste, can turn blue litmus paper red, and are corrosive to metals. Acids conduct electricity in solution and can react with bases in a neutralization reaction to form water and a salt. A common example of an acid is hydrochloric acid, which is found in stomach. Bases are substances that accept hydrogen ions or release hydroxide ions in water. Bases have a bitter taste and a slippery feel, and they turn red litmus paper blue. Like acids, bases are also electrolytes and can neutralize acids. Sodium hydroxide, commonly used in soaps, is an example of a strong base. The pH scale is a numerical scale used to measure the acidity or basicity of a solution. It ranges from 0 to 14, with 7 being neutral. Acids have a pH less than 7, with lower values indicating stronger acidity, while bases have a pH greater than 7, with higher values indicating stronger basicity. For example, lemon juice, an acid, has a pH around 2, while baking soda, a mild base, has a pH around 9. The solutions, mixtures, and suspensions are all forms of matter that involve combinations of substances, but they differ in their composition and properties. Solutions are homogeneous mixtures where one substance called solute is completely dissolved in the solvent. In a solution, the particles of the solute are so small that they are evenly distributed at the molecular level and cannot be seen, even under a microscope. Solutions are transparent and do not separate over time. For example, salt water is a solution where salt dissolves in water. Mixtures are physical combinations of 2 or more substances where each substance retains its own chemical properties. Unlike solutions, mixtures can be either homogeneous or heterogeneous. In a homogeneous mixture, the components are uniformly distributed, like in air, which is a mixture of gases. In a heterogeneous mixture, the components are not evenly distributed, like in a salad, where you can see the individual ingredients. But suspensions are heterogeneous mixtures where solid particles are dispersed in a liquid or gas, but are large enough that they do not dissolve. These particles can be seen with the naked eye and will settle out over time if left undisturbed. An example is muddy water, where dirt particles are temporarily suspended in water but eventually settle at the bottom. Stoichiometry is the branch of chemistry that deals with the quantitative relationships between the reactants and products in a chemical reaction. It involves calculating the amounts of substances consumed or produced in reactions using balanced chemical equations. Stoichiometry is essential for predicting the quantities of materials needed for reactions. Stoichiometry is based on a few key assumptions like law of conservation of mass. This principle assumes that matter is neither created nor destroyed in a chemical reaction. Therefore, the total mass of the reactants must equal the total mass of the products. Balanced chemical equations. Stoichiometry assumes that the chemical equation representing the reaction is balanced, meaning the number of atoms of each element is the same on both sides of the equation. This allows for correct mole ratios between reactants and products. Reactants must be pure. It assumes that the reactants are pure and fully participate in the reaction without any impurities or side reactions that might alter the outcomes. Reactions go to completion. Stoichiometry typically assumes that the reaction proceeds to completion, meaning all of the reactants are converted into products, leaving no excess reactants. In reality, some reactions may reach equilibrium, and stoichiometry is adjusted accordingly in those cases. Molar mass is the mass of 1 mole of a substance, expressed in grams per mole. It is calculated by adding the atomic masses of all the atoms in a molecule. For example, the molar mass of water is approximately 18 grams per mole, calculated by adding the masses of 2 hydrogen atoms, 1 gram per mole each, and 1 oxygen atom, 16 grams per mole.